Hello and welcome to week 10 in geometry. We're going to start with a warm-up. So as always, please make sure you've got your math notebook out and you're ready to take notes in your math notebook. And I'd like for you to start with the warm-up problem. Complete this in your math notebook. So the warm-up this week is just reviewing a vocab word that we have learned. So what does bisector mean in geometry? What does bisector mean? To bisect something. So if you need to do a quick web search, remember Google, whatever web search browser is your friend. So you can type in bisector. And I would also type in geometry because we want to make sure that we're getting the meaning of bisector in the context of geometry. So go ahead and jot down your response in your math notebook now, and go ahead and click on pause to give yourself some time to do that, and then click play to join back. So a bisector, let's go ahead and jot down what it means, is a line that divides something into two equal parts. Again, it's a line that divides something into two equal parts. But what do I mean with something? What could those somethings be? It might be a line that divides an angle. So we can have an angle bisector. We can have an angle, and then a bisector would divide that angle into two equal parts. We can have a line that divides a segment into two equal parts. So if we have a segment and we have a bisector, it's gonna, that doesn't look quite in the middle there, but it does, a bisector is gonna divide something into two equal parts. And remember, those ticks tell me that this segment now is congruent to that segment. So a line that divides something, whether it be an angle or a segment, it's going to divide it into two equal parts. That's what a bisector is. And we're going to be dealing with the term bisector a lot this week, and that's why I wanted to review it. So this week we are going to be investigating and exploring some different types of special segments found within triangles. So Unit 2 has been all about triangles so far. And this week we're going to explore some different types of segments inside triangles. So we're going to look at bisectors of triangles. It's going to include angle bisectors and perpendicular bisectors. Then we're going to look at medians and altitudes of triangles. So those are other types of segments within triangles, as well as looking at the triangle mid-segment theorem. So this recording, remember, I don't have enough time to go through everything. It's going to hit mostly on the first two sessions, which means this last session you're going to really be focusing on the lessons in Schoology. So this recording is really going to focus on the first two sessions. I do also, on the slide with this recording, there is a link to a Google Doc that is a graphic organizer that's going to go over some of the special segments in the triangles that I'm going to go over. So fill that out as you watch this recording. And then just a heads up, next week is the Unit 2 test. So just a heads up that that's coming. Get you thinking about redoing low scoring assignments and studying for that Unit 2 test that is coming your way next week. So again, I do have that Google Doc on the slide with the recording. And in that Google Doc, there's a graphic organizer to help us organize the different characteristics of perpendicular bisectors, altitudes, and medians. So these are three different types of special segments that we can find within triangles. And each of these segments are going to have two of the three characteristics below. They're either going to intersect at a vertex, they're going to bisect a side at a midpoint, there's that term bisect, or intersect the side at 90 degrees. So that, go ahead and open that graphic organizer so that you're ready to take notes and write down each of the characteristics for each of the special segments in the triangle as I go over them. So this is just to get you prepared to take good notes as you go through this recording this week. All right, so we did a little bit of a review of what a bisector is. And now we're going to combine bisector with another term that we've learned in the past, perpendicular. So perpendicular bisector. And it is what it sounds like. So the definition of a let me start over again there. The definition of a perpendicular bisector is a segment that passes through the midpoint of a line at a 90-degree angle. So remember, bisector is going to intersect a segment and divide it into two equal parts. So now these two segments would be congruent. And then we're going to add in perpendicular, which means it also has to intersect, that bisector has to intersect at a 90-degree angle. I'm going over this because I'm going to introduce a new theorem to you, the perpendicular bisector theorem. So here's a nice image or picture of the perpendicular bisector theorem. And what it is it states that any point on the perpendicular bisector of a segment, so this segment right here, this CD, that's our perpendicular bisector. And you can see it's our perpendicular bisector because it's intersected this segment down below, AB, it's intersected it. It's bisected it, so it divided it into two equal parts. We know that because of the ticks. And then it's a perpendicular bisector because it intersects at a 90-degree angle. So any point on the perpendicular bisector is going to be equidistant from the endpoints of the segment. So what that's saying, I'm going to go ahead and highlight maybe in orange. We'll focus on this one. So here we've got a point G, on our perpendicular bisector. So this point has to be equidistant from the end point of the segment that the perpendicular bisector intersected. So the distance from A to G is going to be the same distance from G to B. That's all we're saying, is that the distance between A to G has to be the same distance between G to B. And remember, it can be any point that's on the perpendicular bisector. So if we go up to point E here, we know now that point E has to be the same distance to A as it is to B. So the distance from A to E is going to be the same distance from E to B. That's all that theorem is saying. So let's look at that applied in a problem. All right, so we're going to use the perpendicular bisector theorem to solve this problem. We want to solve for x, by the way, that's what we want to do here. Solve for x in this problem below. So I've got the length of MN, this segment length here is represented by 3x minus 2. Then we've got another segment length that is represented by 6x minus 14. So how can I solve for x? Well, I just learned about the perpendicular bisector theorem. So point N lies on our perpendicular bisector. So remember, this line right here is our perpendicular bisector. So segment NP is our perpendicular bisector because it intersects segment MO. We know that because of the ticks here. We know that point P is our midpoint. And then it intersects at a right angle. So we know NP is our perpendicular bisector. Now point N lies on that perpendicular bisector. And we just learned that the distance between that point on the perpendicular bisector and the end point of the other segment has to be equidistant. So we know now that using the perpendicular bisector theorem, we know that the length from M to N has to be equal to the length from N to O. Well, now we can just substitute in the equations given for each of those segments. So I'm just substituting in those given lengths, and now I have an algebraic equation that I can solve for x. So I'm going to solve for x. I'm going to start getting all my x's on the right side and all my constant terms on the left side. So to do that, I'm going to subtract 3x from both sides, and I get -2 is left over on the left. I've got now 3x's on the right side, and I've still got this 14. Then I'm going to work on solving for x by adding 14 to both sides. I'm going to move all my constants to the left side. -2 plus 14, I'm now at 12, equals 3x. Last step is to divide each side by 3, and I get x equals 4. X equals 4, because 12 divided by 3 equals 4. And I'm done. So I wouldn't be able to set those two equations equal to one another without knowing the perpendicular bisector theorem. So that is our reasoning of why or how we are able to set those equations equal to one another, is that we use the perpendicular bisector theorem to state that these two segments are equal to one another. I'm going to move on to the next slide, so if you need more time, go ahead and click pause. All right, so as we start learning about our three different special segments that I promised you we'd learn about, our altitudes, medians, and perpendicular bisectors, before we start learning about what those are, I want to talk a little bit about intersecting lines. You're going to see some vocab this week in your Schoology lessons about intersecting lines within a triangle. Sometimes they might be outside a triangle. But when we have three or more lines that intersect at one point, these lines are called concurrent. So you're going to see concurrent this week. And then more specifically, the point of concurrency, so that point where all three of the lines intersect, is called the point of concurrency. So that's the point where those lines intersect. So this point right here, that would be the point of concurrency, because that's where all of our three or more lines intersect. This week, when we deal with altitudes, medians, and perpendicular bisector, there's only going to be three of those that are going to intersect, but a point of concurrency is the point where those lines intersect. So when you see that term, that's what it means. Here, this diagram, these lines are not concurrent, meaning they don't intersect at one specific point. So this week we're going to look at points of concurrency, which is where we've got three lines intersecting at one point. All right, so our first type of special segment within a triangle is a perpendicular bisector. So if you've got your Google document, that graphic organizer out, remember I said the link to that is on the slide with this recording. So we're going to start filling out the information on that graphic organizer. So our first type of special segment that we're going to look at is called a perpendicular bisector. We've already talked a little bit about this, but we're talking about it within a triangle now. So if you've got a triangle, there's going to be three of them. But what it is it's a segment that passes through a midpoint. I'm going to change colors here to highlight. It passes through a midpoint of a side of a triangle. So remember, midpoint is just, it divides a segment into two equal parts. So it's going to pass through a midpoint of the side of a triangle, and it also has to be at right angles to that side. So remember I said that each of our segments are going to contain two special characteristics, and there's three of them total, right? So the perpendicular bisector, the two characteristics that it has to have is it has to intersect a side at a right angle, and it has to intersect that side and divide it into two equal parts. So it's intersecting at a midpoint. So there's going to be three perpendicular bisectors because we've got three sides of our triangle. And the point where all the perpendicular bisectors intersect, that point of concurrency, is called the circumcenter. So the circumcenter is right here. It's right here. It's where all three of our perpendicular bisectors intersect, is at the circumcenter. And there's a special property using the circumcenter. That special property is that the circumcenter, so remember our circumcenter, it's right here. Here's our perpendicular bisectors. They're in red. Our perpendicular bisectors are in red, and where they intersect is the circumcenter. The circumcenter is going to be equidistant from the vertices. That's a little confusing because remember our perpendicular bisector didn't start at a vertex. It starts at the midpoint. But the special property of circumcenters is that the circumcenter is going to be equidistant to our vertices. So if we start at our circumcenter and we move out to our vertices, that distance is going to be the same for all of the distances between each vertex and the circumcenter. So let's look at a problem that uses that idea, that theorem. So here, all these So I've got a triangle, and here is the circumcenter. Here is the circumcenter. This is where all of our perpendiculars, bisectors intersect, right here. And we want to use that idea of that circumcenter theorem that I just introduced to you to find the length of AG. So I'm going to highlight AG, what we're trying to find here. So here's A and here's G. And remember, we were told that the distance from the circumcenter out to our vertices will all be the same. So from here to here, here to here, all these distances will be the same. Here's our perpendicular bisectors. But now the distance, once we find where all of our perpendicular bisectors intersect, once we have that point, all the distances between that point and the vertices will be the same. And right here, one of our vertice lengths are given. So if the length from B to G is 13.4, then the length from A to G must also be 13.4 because of that theorem that we just learned. I'm going to go on to the next slide, so if you need more time, go ahead and click pause. The next special type of segment we're going to look at is altitudes. Altitudes. So what two characteristics do altitudes have? Well, the altitude is a perpendicular segment, so it's got to intersect a side at a right angle, and it also has to intersect a vertex. So it's got to intersect, one of the endpoints is going to be at a vertex, and then it also has to intersect a side at a right angle, the opposite side. So we're going to have a vertex, intersection, and it has to intersect the opposite side of the vertex at a right angle. So that is, we got a perpendicular segment and then with one endpoint at a vertex. And that makes it a altitude. I'm going to move on to the next slide, and we're going to talk about if we draw in all three altitudes, where do they intersect? So if we draw in all three altitudes, they're going to intersect at a single point, and it's called the orthocenter. So where we have all three altitudes intersecting, it's called the orthocenter. Now, what's special, the special property of the orthocenter, of our altitudes, is that the orthocenter can be located inside. If we have acute triangles, it's always going to be inside our triangle. The orthocenter might be located on the triangle, and that would only happen when we have right triangles. Or it might be outside of the triangle, and that only happens when we have obtuse triangles. So orthocenters might be located inside, on, or outside of the triangle, depending on what kind of triangle it is. I'm going to move on to the next slide. So if you need more time taking notes, go ahead and click pause. Medians, our third type of special segment of triangles, the third one is called the median. And a median always has a segment that intersects a vertex, and on the opposite side intersects the opposite side at the midpoint. So remember, it's going to divide it into two equal sides. So we're connecting a vertex to a midpoint. Vertex and a midpoint. And that's what makes a segment a median. So now if we draw in all three of our medians, where will they intersect? It is a point called a centroid. So a centroid is where all three of our medians intersect. And there's a special property that we're going to use to solve problems that deals with centroids. So remember, a centroid is where all three of our medians connecting a midpoint to a vertex, where all three of those intersect is at a centroid. And there's a special property. So when we look at a centroid, or I'm sorry, just one of our medians, you notice that there's a point of concurrency at the centroid, and there's always going to be a longer side and a shorter side when we look at our median and that centroid point. There's a longer side and a shorter side, and there's a pattern that occurs between that longer side and that shorter side. There's our longer side, there's our shorter side, and this is it. So let's look at this one right here. So AP is going to be equal to, this longer side here is going to be equal to 1/3 of the entire segment. And this works for all of them. So BP, the longer side, is going to be equal to 2/3 of BF, the entire segment of our median. So we're going to use that idea and that pattern to solve some problems this week. One other fact about centroids, so remember I said that each median always is, there's a point of, right there, that's our centroid, that divides our median up. So the longer side is going to be also 2 times longer than the shorter side. And that's going to also be helpful in solving problems. So let's go to the next slide and solve a problem using centroid problems. So I've got a triangle. And each segment, what do we have here? We've got a segment that intersects a vertex, and then it also intersects the other side at a midpoint. It bisects it. So these are all medians, and they intersect at the centroid. So in this triangle, we're given some lengths. We're given the length that BG, and if you want to try and solve this on your own first, go ahead and click pause and try to solve it on your own, and then you can check your work with mine. So the length from B to G is going to be 10, and we're also given the length from A to E, so this entire segment, A to E, is 12. Using that information, let's find lengths GF and lengths AG. So can we find GF knowing that from B to G is 10? Remember what I just told you on the previous slide? That longer side is going to be 2 times the length of the shorter side. So if we know that we can use the information, AF is going to be equal to 1/2 of the length from B to G. So 1/2, we now know BG is 10. 1/2 of 10 is 5. So the length of AF is going to be 5. What about the length AG? We want to find length AG. Well, that we can use this idea here, that the length of the longer segment from the vertex to the centroid is going to be 2/3 the length of the entire median. So we know that the length of A to G is going to equal to 2/3 the length of the entire median. And we were given that the length of the entire median was 12, so 2/3 of 12 is what? It's equal to 8. So the length from A to G is 8. I'm going to go on the next slide, so if you need more time, go ahead and click pause. So which of our 3 segments has a perpendicular bisector, or it intersects the side at a right angle? Let's just kind of compare them all. Perpendicular bisectors do, and so do altitudes. Altitudes and perpendiculars have to intersect one of their sides at right angles. Which of our 3 segments has to intersect a side at a midpoint? Well, bisector, we know bisector means intersects at a midpoint, so perpendicular bisector has to be one. And then the median is going to be our other one, which leaves a vertex. Medians have to start at a vertex, and so do altitudes. So we see that each of our segments have 2 out of these 3 characteristics. I'm going to move on to the next slide, so if you need more time, go ahead and click pause. And let's put it all together, and let's identify. We've got a couple different segments in here: a red segment, a green, a blue, and this light blue here. So which segment is the median? So what is the median again? So remember, a median has to start at a vertex. So right away we know this red one cannot be a median. So it has to start at a vertex. Okay, so right here to starting at vertex. And then it also has to intersect at a midpoint. So this green one starts at a vertex and intersects the line at a midpoint. So this green one is the median. And if you want, go ahead and click pause and try to find the altitude and perpendicular perpendicular bisector on your own. Go ahead and click pause and try and finish this out on your own. The altitude, remember an altitude, it starts as a vertex and intersects the opposite side at a right angle. So it starts at a vertex and intersects the opposite side at a right angle. So that would make this our altitude because it starts at a vertex and intersects the opposite side at a right angle. And last, which segment is our perpendicular bisector, perpendicular angle, and intersects at a midpoint. So it makes it that red segment here is going to be our perpendicular bisector, with really the definition given in the name of the segment. So lots of different properties, lots of different theorems that you've learned that will help you solve problems this week. So we're ready for our key phrase assignment. Let me put that up. So we learned 3 special segments within triangles this week. We learned about perpendicular bisectors, medians, and altitudes. We learned lots of different things about them. We learned that those 3 segments will intersect inside or maybe outside of a triangle, and we learned what those specific intersections were called. But this key phrase assignment, I want you to just focus on 2 of the segments that we learned about, medians and altitudes, and tell me the difference between each of those. Tell me the difference between a median and an altitude. So I hope you took good notes as you watched this recording, filled out that graphic organizer. I'd love to see that when you submit your notes this week. Have a great rest of your week, and let me know if you need help with anything.